We probably can get started here. I want to welcome everybody to the March edition of our Center uh, Environmental Health and our P30 Southern California Environmental Health Science Center seminar series. The first Friday of every month, typically we spend time speaking with a colleague, uh, share with us ideas and insights about their research, their work, their perspectives on things going on in the world of environmental health. Um, we will have a few more of these seminars. We typically run with the academic year, so we'll run through June. Next month's speaker, for those who are planning their schedule, will be on April 2nd, the first Friday, will be Lisa Krohn from Kaiser Permanente, Northern California, who does work in autism research. And so we'll have, for all of you interested in sort of neurological aspects of exposure, who want to be attending that one. Today we have a person who probably we could spend the hour talking about in terms of providing the adequate introduction for him, but I won't do that. I'll just defer to our department chair from preventive medicine, Howard who actually has known Howard Frumkin for many years and can speak, sort of as both a friend, a colleague, and a co-investigator. And so, Howard, please introduce Howard.
My big pleasure. So let me just relay a story. Many years ago, Howie Frumkin and I, my fellow Howard, were at a party, and a phone call came in, and Howie picked up the phone. And the person on the other side said, I'd like to speak to Howard, please. And he says, well, which Howard? And this person said, well, oh, the Howard who went to Brown University and then went off to medical school, took a year off, went to the Harvard School of Public Health, and then did internal medicine and then occupational medicine, that Howard. And then Howard said, can you be a little bit more specific? Because it turns out we were together for a lot of that, joined at the hip. But of course, Howard then went off to had this fabulous career. For those of you who've been able to follow it, Howard was the chair of environmental health at Emory. Then he went to the Centers for Disease Control and led the National Center for Environmental Health. Then he came to the University of Washington, was the dean of the School of Public Health there, and then went on sabbatical and went on to lead the Planetary Health program at the Wellcome Trust. And along the way, Howard has had a spectacular career opening our minds to what's happening on a global level, certainly for climate change. And he started the Global Environmental Center at the University of Washington. And among his many books are his last two, which are about planetary health. And I could go on and on. I remember as a department chair, we used the textbook that he edited on environmental health as our leading textbook in teaching students. So he's had a huge impact on our field. He's been one of the big thinkers about where we're going. And he's going to talk to us today about planetary health. This, of course, is something that we've started to embrace in our own Southern California Environmental Health Center, looking at some of the climate change things that are happening here in California and working with President Folt's sustainability initiative. So we're all eager to hear what Howard has to say on this topic. So may I present to you Howard Frumkin.
Thank you, Howie. What a nice introduction. I'm really flattered. I thank you all for attending this morning. I hope you're having as good a day as I'm having. I spent the morning making some new friends and getting together with some old friends and learning a little bit about what your program at USC is all about. And a morning doesn't get any better than that. It's very nice to be here. Thank you. My topic is planetary health with the provocative subtitle, I hope, Environmental Health 4.0. Before going on, I'd like to acknowledge that I'm speaking today from Seattle, the traditional unceded land of the Coast Salish peoples, the land that touches the shared waters of all tribes and bands within the Duwamish, Puyallup, Squamish, Tulalip, and Muckleshoot nations. We honor and respect those peoples. My agenda today is relatively brief. I've just got three things I want to cover. I want to introduce the planetary health paradigm. I want to give a few examples, and depending on how timing is going, it'll be either two or three or maybe a couple more. And then I want to close by talking about hope, because this is a field of environmental health, and in fact, a field of public health in general that can either trigger despair or it can trigger hope. And I want to close by making the case that we should all be about hope. So to begin by introducing the planetary health paradigm, I'm going to ask you, although you may be a health professional, as pictured on the left, I want you to channel your inner historian and your inner ecologist, because those are the two frames that help us understand planetary health. And in particular, I'm going to introduce 8 key concepts that I think it's more than any speaker should ever try to get across, but I'm going to try. And I think these concepts, the great acceleration, the concept of deep time, the Anthropocene, planetary boundaries, oh, it's there twice, only 7 key concepts. The concept of the typographical error, the donut, ecosystem services, and polycrisis. And all of that, I think, will give us a firm foundation in planetary health. So let's begin by channeling your inner historian. The story begins here at the bottom of a Scottish coal mine in 1860. Now, by the time this picture was drawn, coal had been used for quite some time, but it was ramping up to a huge scale in the UK and elsewhere in the world as the Industrial Revolution took off. I like this picture because the guy sitting there at the bottom of the coal mine wearing a white wig, totally inappropriate for a coal mine, seems to be lighting a cigar or a pipe, which is a reckless thing to do in the presence of all that methane gas, and actually a nice preview of the reckless insouciance that was to characterize energy policy for many decades to come. So the story may begin here in the bottom of this coal mine, or it may begin here. This is the Drake well in Pennsylvania, the first commercial oil well in the US, drilled in 1859. Well, together, the coal and the oil ushered in the availability of unprecedented, enormous amounts of energy available for society to utilize. And sure enough, as history moved on, energy consumption grew dramatically. You see a picture here. There's a bit of a time lag. Let me see if I can get my arrow. A bit of a time lag from the mid 19th century when exploitation of coal and oil began. But within decades, the use of energy by humanity grew to unprecedented levels. And that triggered lots of other historical developments. It triggered the growth of the world population in an exponential way. And now you can see that human population was relatively stable for much of history. The birth of agriculture helped. Population began to grow at a slow rate. But when it really took off was right about here in the last couple of centuries, thanks to the availability of all that energy. This is a picture of economic activity, which closely parallels the growth of population. This is world GDP, and it skyrocketed. In fact, by almost any measure you can look at, whether it's water use or transportation or fertilizer consumption, paper production, the number of McDonald's stores, the number of trips we take, the human enterprise has scaled up dramatically in the last century and a half, and especially since the end of the Second World War. This is a trend called the Great Acceleration. In many ways, it's been a great time for human health. As you can see here, illiteracy has dropped to unprecedented low levels. Poverty has dropped to inequitably distributed. We still have too many poor people, but poverty has dropped dramatically. Child survival has increased and life expectancy has increased. So this has been, in many ways, a good time for human health and well-being. On the other hand, it's come at a price, and the price is being paid by our planet. In some ways, we've been mortgaging the future for the benefits of the present. If we consider the impacts on the planet, it's almost difficult to get our minds around it. But scale the planet to the size of a soccer ball and consider the fact that the biosphere, all of life, 20 kilometers thick, is about as thick relative to that soccer ball as a sheet of cellophane wrapper, a very thin layer around the surface of the planet. Consider the life within that biosphere. All in all, it comprises about 550 gigatons of carbon. And you can see in perspective that the animal kingdom is a small fraction of 1% of all of life on Earth. And if we drill into that animal kingdom, you can see that it's mostly insects. There are lots of fish. And here we are as humans, a small fraction of 1% of the animal kingdom, which is a small fraction of life on Earth. And now to put that in temporal perspective, as well as in spatial perspective, here's a picture of the entire life story of the Earth. It begins about 4.5 billion years ago. Come forward through all of geological time. Primates show up maybe 50 million years ago. Homo sapiens shows up maybe a couple of 100,000 years ago. And here's a blow up of the last little section of the history of the Earth, perhaps most evocatively described by John McPhee in Annals of the Former World. Consider the Earth's history as the old measure of the English yard, the distance from the king's nose to the tip of his outstretched hand. One stroke of a nail file on his middle finger erases human history. So here we are, a tiny fraction of life on Earth inhabiting this remarkably thin biosphere, having showed up very, very late to the party and inhabiting it only for a small amount of time. Is it possible that we've changed the course of the planet's history? Well, it is. We live on a different planet than our grandparents inhabited. We've changed the chemistry of the atmosphere, as you know, with carbon dioxide being the best known example of that, but other greenhouse gases also. We've changed, as a result, the surface temperature of the Earth. We've changed the chemistry of the oceans. We have changed the nature of life on land with tropical forests, with appropriating 40 to 50% of the Earth's land surface to grow our food, and having triggered the sixth great extinction, which we're now in the midst of. This is a different planet than our grandparents inhabited. So different that geologists have posited the beginning of a new geological epoch called the Anthropocene. Shown here in this cartoon is just the last few hundred years, representing a phase shift from the Holocene, the conditions that prevailed with relative stability for the last 12,000 years or so, and in which civilization developed. The Anthropocene is marked by the fact that humans define much of the planet's conditions now. And that in turn has given rise to the notion of planetary boundaries. This is kind of an iconic picture in the planetary health field that you may have seen before. The notion is that there is a safe zone within which life can continue sustainably with regard to climate, with biodiversity, with land use, with fresh water. Novel entities refers to persistent chemicals in the environment, stratospheric ozone levels, and so on. There's a safe zone for all of those. And there is a danger zone, which if we enter, could trigger irreversible changes and degradation of Earth systems. So for several of these, we remain in the safe zone. For several, we're in a zone of uncertainty, signaled by the yellow here, indicating that we don't really know how far we've come relative to planetary boundaries. And with regard to biodiversity and biogeochemical flows of phosphorus and nitrogen, we have already brought enormous phase changes that may be irreversible. So this is the notion of planetary boundaries. It's a little contentious. People argue that some of these are more regional than global. People argue that in some cases there aren't lines in the sand that we can define as cutoff points. But the notion that we can transgress boundaries is very much at the heart of planetary health thinking. And the notion that if we transgress those boundaries too much, the Earth may not be inhabitable for civilization as we know it is very much a reality. Now, we are health people, and you may look at this picture and you may say, well, that's an interesting statistical model, but where are the people? That looks like something that Earth scientists would do. So that's a great question. Let's redraw it so that it looks like this. Same picture, you got ecological ceiling above which we don't want to go. That would be overshoot. And here are the same parameters. But now let's put into the center of it the people. And here you've got human needs: energy, water, food, health, education, peace and justice, political voice, and so on. This defines a floor, if you will, below which we don't want to go. That would be a shortfall. So this is the donut economics model put forward by Kate Raworth at Oxford. It's an economic model, but it's very much a model that aligns with planetary health thinking. The notion that human needs and human privileges, if you will, exist within the context of planetary limits. If we don't exceed planetary limits, and if we don't fall short of human needs, then we're in a safe and just space for humanity called the regenerative and distributive economy. Now, a related concept to all of this comes when we think about the ways in which the planet provides us with services. This is the notion of ecosystem services. You may be familiar with this. This comes out of the Millennium Ecosystem Assessment. The idea is that the natural world provides us with supporting functions, such as, for example, soil formation, provides us with provisioning functions by giving us food and water and other things that we need. Regulating functions, think of a mangrove forest blunting the impacts of coastal flooding or coastal storms. And cultural functions, think of the joy and restoration you feel when you go to a natural setting. Now, according to the Millennium Ecosystem Assessment, all of those ecosystem services can be mapped to human needs, the constituents of well-being, as you see here. So it's a complicated picture. The thickness of each arrow reflects the intensity of the linkages between an ecosystem service and a component of human well-being. You can see that security, basic materials for good life, here's health, good social relations. The planet provides us with our needs in each of those respects. And of course, this is a little bit oversimplified because basic material for good life in turn is required for good health. So here's the notion of ecosystem services, reinforcing the concept, which is at the core of planetary health, that we can't have healthy people without a healthy planet. We depend on that planet. But here we are living on a very much changed planet, as I mentioned before, from the ones that our grandparents occupied. Climate change, perhaps the best recognized of these. But even if we didn't have a changing climate, we would still want to be talking about planetary health because other planetary changes, biodiversity loss, changes in the way we lose land, drastic reductions in soil availability, faster than the Earth can regenerate soil, altered phosphorus and nitrogen cycles, depleted fisheries, chemical contamination, loss of fresh water, atmospheric aerosol loading, and the fact that our small but highly influential species is now crowding into smaller and smaller places. All of those represent the challenges of a changing planet. But you'll recognize looking at this picture that it artificially separates these things from each other. In fact, these challenges overlap with each other, as exemplified by this picture that I'm sure you've all seen, the fact of the COVID pandemic and the restrictions that are required in the face of global climate change. There is such interaction among all of these challenges that the picture might be better shown like this, as a systems diagram in which, to quote the first law of ecology, everything is connected to everything. Now, two more features of the challenges that we face, and then I'm going to move on to some examples. One feature is that not only are these changes occurring, but they're occurring faster and faster. They're accelerating. I'm going to show you a series of relatively rapid pictures to demonstrate that point. Here's a picture of biodiversity loss. These are vertebrate species losses. And what I want you to see is the way that the curve has become more and more steep over recent decades. The loss of vertebrate species is accelerating fast. This is a picture of insect population declines over recent decades, very high numbers and accelerating. This is a picture of Antarctic sea ice loss. And as you can see, the slope is becoming steeper and steeper as this accelerates. This is a picture of glacier loss globally. It is accelerating. This is a picture of weather-related catastrophes over the last 4 decades or so. And as you can see, those catastrophes are increasing at an accelerating rate. All of this foretells the possibility of reaching tipping points, such as, let's look at the loss of Arctic sea ice, which can in turn trigger changes in the Atlantic circulation as cold water from Arctic ice pours into the North Atlantic and slows the Gulf Stream. The loss of coral reefs, the loss of boreal forest, these tipping points, which we are approaching, but at a speed that we can't know, could signal irreversible changes in the planet. So this is a rather urgent situation that we face. And finally, one more image to connote the pace of change relative to how we're living our lives. This is a picture of various pathways to limit global warming to 1.5 degrees. Each of these lines reflects a different model, shared socioeconomic pathways, different assumptions about the ways in which we adjust and the ways in which the Earth systems respond. But any of these is a plausible pathway to get to 1.5 degrees global warming. The point I want to show you is that every one of these pathways contemplates dramatic CO2 emissions reductions starting about now, arriving at a 50% reduction of CO2 emissions by 2030 and reaching net zero by 2050. Every pathway we can contemplate requires those assumptions. But emissions continue to rise. We are not anywhere near reducing our emissions by 50% a decade from now. So in the health sciences, we have a name for this situation. It's called emergency. Very rapid and accelerating pace of change. And the final feature that I want to mention is our own cognition as a species. If we were hardwired to think long-term instead of short-term, if we were hardwired to tackle complexity instead of reduce things to simplicity, if we were hardwired to think about future generations, we might be better equipped to address these challenges than we are. But in fact, we're not. So we have to overcome some of our own cognitive limitations. Think more in terms of solidarity and less in terms of tribal affiliation. Think more in terms of complex systems than in simple solutions. And that is part of the challenge that we face. So with all of that as background and context, what about this field of planetary health? Well, I'm going to oversimplify history, if you'll bear with me, and suggest that our field of environmental health has evolved historically in several stages. What I'll call planetary health 1.0 is the age of sanitary engineering, industrial medicine, still a very important part of our field. Every health department has in it people who are very good at restaurant inspections and septic tanks, and we need them there. That's the foundation of environmental health. 2.0 would be toxicology and epidemiology, what a lot of us were trained to do. And I'm showing Rachel Carson here as the emblematic voice there. 3.0 is when we understood that there are social dimensions to environmental health and that inequities have to be at the heart of what we do. And 4.0 is when we expand our view to understand that all of environmental health is embedded in ecological and earth systems. And that context has to be a part of our thinking about environmental health. So how has the field arisen? Well, just a few years ago, there was a manifesto published in The Lancet, shown on the left, followed by a commission report shown on the right that kind of is the formative document for planetary health. A Planetary Health Alliance based at Harvard started up in 2016, headed by Sam Myers. Academic efforts in a number of places around the world have grown up since then. These are just a few examples. London School of Hygiene here. This is the University of Sao Paulo in Brazil here. This is Pompeu Fabra University in Barcelona. This is the Charité Hospital in Berlin. So sort of a growing worldwide effort of programmatic initiatives. And we now have a couple of textbooks that I was lucky enough to help pull together. So it's beginning to look like a field. Meetings, organizations, courses, even degrees, just like real fields have. The definition of planetary health that most people use comes from this commission report. It's a little bit verbose and you can read it yourself, but to cut to the chase, the health of human civilization and the state of the natural systems on which it depends. So it's a composite approach to Earth systems and human health. Let me work a few examples to show you how it looks in practice. I'm going to ground these examples in the ways we live, beginning with the energy we use, moving to the stuff we make, and then to the food we eat, some of the basic components of our lives. Well, when it comes to energy, the obvious example is climate change. And I actually don't want to talk about climate change, partly to illustrate the fact that there's a lot more to planetary health than climate change, and partly because I think it's probably a quite familiar topic to all of you. But I do, before moving on, want to make one point about climate change. You know the basics that in parallel with the increased use of energy that I showed before, most of it from fossil fuel combustion, carbon dioxide emissions have risen over time, and the level of carbon dioxide in the atmosphere has risen over time so that it's well above pre-industrial levels. And we now understand fairly well that there's an inventory of health impacts from climate change shown here. This is a 10-part inventory. Different people have different ways of depicting this, but heat, severe weather events, worsening air pollution and allergies, the infectious diseases, threats to the water and food supply, all of the threats that climate change brings to health that you well know. The one point I want to make about climate change, because it's a fundamental point for all of planetary health, is shown here. This is a picture of the carbon footprint of Americans in relation to household income. And what you can see is that the higher the household income, the higher the carbon footprint, indicating that those of us who are the most fortunate Americans up at this end of the spectrum have very, very big carbon footprints, not only bigger than those of most of the world, but bigger than those who are less fortunate among us. There is an inequity built into the contributions to climate change. And that's true on a global scale too. The richest 10% of the global population accounts for almost half of total lifestyle consumption emissions, and the poorest 50% only contribute about 10% of emissions. That's what gives rise to this diagram that you may have seen. This is a density equalizing cartogram with the size of each country drawn to reflect a particular parameter. At the top, carbon emissions over 50 years, with a big bloviated United States and Europe, and a teeny little, almost vestigial Latin America, Africa, South Asia. But when you look at climate-related deaths, you see the reverse pattern with very disproportionate impacts on Africa, South Asia, and very small impacts on wealthy countries of the world. So equity, 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 very important, not only in climate change, but across the planetary health arena. Let me drill into a different aspect of energy, not burning fossil fuels, but dams, because they illustrate some of the planetary health thinking that I'd like to leave you with today. Well, dams are good in lots of ways. This is a picture of the greenhouse gas emissions of various sources of electricity. And way down there is hydroelectric, some of the lowest carbon means of producing electricity that we know. Now, dams are a familiar part of life. Here in my part of the world, this is a picture of the Columbia River Basin, and each of these little dots represents a dam. You can see that this is about a fully built out river system. So much, in fact, that we're now taking down some dams in order to restore salmon habitat. But fortunately, almost all of our electricity in the Pacific Northwest comes from hydro, so it's relatively carbon-free electricity. Now, dams are a big thing. We have almost 3 million dams in the world. Over 50,000 of them are considered large dams. Most of those are for irrigation and flood control, but about 3,500 of them are sources of hydroelectric energy. And that number, again, are now being planned for construction. In fact, there's a global boom in dam construction that you can see depicted here. This is a picture of a couple of regions of the world that exemplify that trend. And what I want you to see is that the purple dots are operational dams. The red ones are planned and the yellow ones are under construction. So you can see here very graphically how the number of dams in the world is rising fast, leaving fewer and fewer of our river systems undammed and naturally flowing. Now, dams are in many ways good for health by providing clean energy, but they come at a cost, and there are complex trade-offs exemplified no place better than at the Three Gorges Dam, one of the biggest in the world, 2.3 kilometers long, providing vast amounts of energy, replacing 20 coal-fired power plants. But more than 1 million people were displaced. Whole towns and cities had to move. It was done in an intentional way, so nothing catastrophically fast happened, but nevertheless, studies have shown considerable amounts of stress, mental health disorders, and other problems related to the displacement of people. And that's only one of the health impacts of dams that we need to reckon with. We do get clean electricity, we get dependable water supply, irrigation, flood control, but we also get a number of risks, some that are direct, like infectious disease risks, population displacement, as I mentioned, some that are indirect, like altering river hydrology, actually altering the fluxes of a number of substances, some of them toxic, increasing methane emissions and forming toxins such as methylmercury. So complex trade-offs, and this is one of the lessons of planetary health. Trade-offs between health benefits, direct and indirect, and health risks, and also the fact that if we think long-term and anticipate the fact that hydrology is changing with climate change, that many river flows will be diminishing and or catastrophically increasing with severe rainfall events, dams will function differently 50 years from now than they do now. And so that's going to be a part of our planning and thinking about dams, affecting all of our thinking about risks and benefits. Next example, the stuff we make. And let me talk about plastics as the example here. Now, you're all well aware that plastics are polymers of various monomers, shown here. We use plastics for almost everything in our lives. I think that everybody who's on this webinar can look around and you'll see some plastics within reach of where you are. You may be wearing them, you may be sitting on them, you may be leaning on them, as I am. Plastic production has become a marker of the Anthropocene era. World plastic production ramped up after the Second World War to very, very high values. We now make more than 300 million metric tons of plastic each year, or about 40 kilograms for each man, woman, and child. That means that on average, each of us now alive will account for over 2,800 kilograms of plastic production over the course of our lives, or 30 or 40 times our body weight. What are the plastics used for? Well, you can see here a mixture of packaging, consumer goods, construction, automotive, and so on. Very ubiquitous. And we expect that plastic demand will increase significantly in coming years, especially as prosperity continues to grow in low-income parts of the world. So this is a big and growing thing. Now, plastics are very persistent. This is a picture of the lifespan of plastics. Look at plastic bottles up here with a mean lifespan of between 50 and 1,000 years. If the workers who had built the Great Wall of China or Machu Picchu or the Taj Mahal 5 or 6 centuries ago had sipped water from plastic bottles during their breaks from work, there's a good chance those plastic bottles would still be around somewhere. Sunlight may degrade plastic, and we're learning that sunlight may degrade plastic a little faster than we thought. But the point remains that plastic is enormously persistent. So what do we know about where all that plastic that's been manufactured so far has gone? Well, here's a picture showing on the black curve the total amount of plastic that's been made. Here are the components of it. The red shows discarded plastic. The green shows incinerated plastic, and the blue shows recycled plastic. So the vast majority of it, as you can see here, has simply been discarded. By one estimate, for every human being now alive, there is somewhere in the world about 1 metric ton of plastic. Where does it go? Well, some of it's in landfills, some of it's in waterways. This is a common and heartbreaking sight for any of you who've traveled to major cities in the developing world. Plastic generally floats when people toss it in waterways. So it travels with currents, it accumulates in eddies, it forms patches that can be as large and imposing as islands. From streams, rivers, and harbors, the waste winds its way to oceans, an estimated somewhere between 5 and 13 million tons of plastic entering the oceans each year. And driven by wind and current, the plastic seems to go everywhere. So what begins looking like a local problem becomes a global problem. Plastic has been found in the deepest ocean trenches, in Arctic ice, in Mongolian mountain lakes, on remote island shores. The world's ocean systems tend to concentrate plastic waste in the 5 great ocean gyres that you see here. Interestingly, the highest concentration of plastic debris ever measured on a beach was on remote Henderson Island on the western edge of the South Pacific Gyre, 5,000 kilometers from the nearest significant human habitation. While the plastics permeate ecosystems, we now know, for example, that a lot of birds ingest bits of plastic, but they can't digest it. And so we're seeing more and more plastic accumulating in the bodies of seabirds, an estimated 90% of them now being found with plastic in their bodies. So let's drill into this plastic waste. It comes in different sizes from macro to nano. The macroplastics can have devastating impacts on wildlife, as you see in the picture of this turtle, unlucky enough to be caught up in a 6-pack holder. I buy all my beer in paper cartons now, not in 6-pack holders like this, all the way down to micro and nanoplastics that are extremely small, some that are primarily components of clothing or cosmetics, some that form from degradation. And what's important about that is that the microplastics are ingested by small organisms. Here's a picture of polystyrene being taken up by various species of zooplankton. The green fluorescing images here are the polystyrene, and then it enters the food web. So here you have nanoplastics and microplastics entering not only plankton, but even bacteria, which are taken up by larvae and by filter feeders. We talked about oysters in one of the early sessions this morning, up the food web to fish, to seabirds, to marine mammals, and then to top predators like us. And sure enough, studies are beginning to show that in our food supply, plastic is commonly found. This is a recent study of fish and shellfish from markets in Indonesia and California, which found plastics in a quarter of the individual fish specimens tested and in about half the species that were tested. So when we eat fish, we're eating plastic. And it's not just fish. In almost every food group that's been studied for the presence of plastics, they are found. Sea salt, honey, beer, bottled water, and then a number of fish products. So you know where this is going. If you follow the plastic through the pipeline, studies have also, one study so far has shown that in every fecal sample studied in Europe, plastics were found. Plastics are everywhere. Now, why do we care about this from a health point of view? Well, plastics are mostly polymer, and the polymers are relatively inert. But on average, 7% of plastics consist of added chemicals, plasticizers, flame retardants, and so on, many of which are persistent organic pollutants with endocrine disrupting and other biological effects. Not only that, plastic molecules are very efficient adsorbers of synthetic organic chemicals to their surfaces, and so they become vehicles for the transport of those organic chemicals as well. All of that contributing in large but not completely quantified ways to endocrine disruption and to other biological effects. And this too becomes a global problem because persistent organic pollutants, in part thanks to plastic migration, are transported around the world as indicated by this cartoon. And that's happening in ways that are being accelerated dramatically by climate change. One recent study of Inuit people in the Canadian Arctic found that those with the highest blood levels of PCBs were 1.9 to 3.5 times more likely to have diabetes than those with the lowest levels. And again, these are indigenous people who never lived anywhere near the sites of manufacturing or incineration of plastics, but these have worldwide reach now. Now, lest I seem to be beating up on plastics in a one-dimensional way, let me say that there are some good things about plastics, as suggested by this cheerful cartoon from the early post-World War II years. Plastics have a lot of use, as shown here in the kitchen. Well, a really great review paper just came out from the London School of Hygiene, looking at the role of plastics in the food system and dividing that role into three domains. The domains are human health, food security and economics, and the environment. And the benefits show up in substantial part here. Plastic may be a way to retain the freshness of foods, to retain the nutrient contents of foods, to reduce food loss and food waste, which accounts for 30% of the food produced in the world. So there are real benefits to plastics. The planetary health approach would say, let's look at the risks, let's look at the benefits, let's do that in the most comprehensive way we can, looking at environmental impacts as well as health impacts, and let's chart the best path forward. Well, in fact, this review looked at the body of research that attempts to do that. Let me just have you look at the part on the right here. These are the outcome domains. They looked at over 3,300 studies looking at the impacts of plastics on three domains: food security, human health, and environment. And I look at the overlap here. A number of the papers looked simultaneously at food security and human health. Few of those looked at the environment. And the overlap space here between human health, food security, and the environment is very small, illustrating, unfortunately, the reality that so much of our science is relatively siloed, and so little of our science looks in a cross-cutting way at the many components of planetary health. So a lesson from planetary health is look at the intersection spaces, look at complexity, and try to understand the role of environmental exposures in all their complexity. Let me work one more example from the food space, and this is the challenge of nuts. Now, nuts are good for health. There's actually a lot of nutritional literature showing that nuts help health, and nutritionists love to recommend nuts, calling on literature like this. Almonds are good for cardiovascular health. Walnuts are great for the gut microbiome. Cashews increase your HDL cholesterol, and so on. So lots of benefits of nuts. Now, if you were a nutritional researcher, what kinds of questions might you be asking about nuts? Well, you might ask what components of nuts promote health, uh, which are the chemicals, the active ingredients? Can we make healthier nuts? What's the optimal dose of nuts? How do we persuade people to make behavioral choices to eat more nuts? But I'm going to suggest that if you're a typical nutritional researcher, one question that you would rarely ask is where do nuts come from? The upstream question. Well, we all know the answer to that. They come from the store. You buy them in little plastic bags and you take them home and you eat them. But actually, if you go upstream from there, nuts come from beautiful places like this almond orchard or this walnut grove. Where do they come from in the world? Well, this picture shows that almond production is 3/4 of almond production in the world comes from the US. And with walnuts, you can see that a large portion comes from the US. China has most of the global market there, or half of it anyway. But we are very big nut producers. So where in the US do nuts come from? Well, essentially 100% from California, at least for pistachios, for almonds as shown here, and for walnuts as shown here. Peanuts still come from elsewhere. Now, tree nuts are a big thing. The one of the major crops in California, they surpass grapes as California's top value crop. #1 agricultural export from California. California accounts for very large shares of global market. So if a nutritionist comes along and says we should all eat more nuts, that has implications for California, doesn't it? Well, let's think about that. This is a picture of the water footprint of various foods. And you can see that beef has the highest water footprint of any, but here come nuts, #2. So when you grow nuts, you use lots of water. And when you export nuts, you're essentially exporting embedded water. Now, what do we know about California as a place to do that? Well, California in the recent past has been facing a shortage of water, well known to all of you, better than to me. And if we look at forecasts for coming years, what's predicted with climate change is more chaotic weather extremes, more severe droughts, and less water from snowmelt as the snowmelt diminishes. So it might seem like pushing for more nuts in the global diet when we are currently growing our nuts in water-stressed areas might not be a good match. And not only that, there's an additional set of implications from the growth of so many nuts in California. Nuts are a fairly pesticide-intensive crop, as shown here with data from the California Tracking Program. And with climate change, it's very likely that pesticide use will have to increase because of changes in pest ecology, fall-offs in pesticide efficacy, changes in pesticide use patterns. So growing a lot of nuts in a place that is water stressed and where climate change will have substantial impacts collides with the idea that we should be recommending a lot more nuts in people's diets. The solution here is to think as systematically as we can about how we feed the planet, which crops we recommend, and how we grow those crops, how and where we grow those crops. Let me work one more example, and then I'm going to get into some closing comments about hope. And the example I want to work is on desertification. And I'm doing this at my own risk because some of the best expertise on the salt in the sea comes from right there in your department. And I want to recognize and salute the good work that's been done there. But I want to talk about desertification in a different place. I want to take us to Kazakhstan and Uzbekistan, where the Aral Sea sits on the border there. Now, the Aral Sea is not nearly the same Aral Sea it was 50 to 70 years ago. What happened was that the Soviet Union in the post-World War II years decided to grow cotton and rice in the Aral Sea basin. And so they diverted the two rivers that feed the Aral Sea and used the water for irrigation to grow crops intensively. That diversion of water led to a shrinkage of the Aral Sea. And this looks even more dramatic than the Salton Sea when you see it from the air. Here it is, 1977, all the way through year by year to 2013, where it is a mere shadow of its former self, giving rise to some phenomenally evocative photographs of old ships left on a dry seabed. This was an amazing transformation in land use driven by agricultural ambitions. Well, not only did the Aral Sea shrink as the crops were grown, but the soil was depleted by poor agricultural practices requiring the intensive use of pesticides and fertilizers in that crop basin. And the shrinkage of the Aral Sea, meanwhile, led to salination of the soil, and the shrinkage of the sea also led to formation of desert. So with all of that, we get enormous dust storms, something that I know you're familiar with from the Salton Sea, but that happens on a much bigger scale here. Here's the remnants of the Aral Sea, and this is a satellite picture of a dust storm moving westward, full of dust and salt and pesticides in the air. Uh, Also, the loss of the Aral Sea has led to enhanced regional climate change because the climate system there is much less resilient than it used to be. So this is kind of a systems picture of how agricultural decisions and land use changes interacted with human health. Now, that has led to a changing pattern of severe dust storms in Middle Asia. Here's the Aral Sea up in this area, and the reddish areas reflect the downwind severe dust storms just in 1 year. But it's really changed the pattern of dust storms. And this is exemplary of a pattern of dust formation and dust movement globally. This happens in predictable ways. African dust transported to the Caribbean and North America along this pathway, and so on. So much so, this is such a global scale, widespread problem that you see headlines like this in the Indian Express, how a dust storm from Iraq, Kuwait, and Saudi Arabia came all the way over to India and accounted for high levels of dust in India. These dust storms can be very dramatic, as shown here in a picture from Dubai. Diverse toxic components and diverse effects on health. So once again, planetary health thinking would have us not just look at the toxic effects of the components of inhaled dust, but at the upstream decisions, well-intentioned decisions. Let's produce more food. Let's feed more people with healthy food. But if you don't think about those things in a systems-based way, spanning agronomy and health and hydrology, then you don't get the right answers and you have unintended consequences. Well, I've given you some pretty grim news, some bad news, and I probably made you feel pretty bad. So let me begin to turn things around. I'm going to give you one more quick example from Planetary Health and then turn to hope. The one more example is the Diama Dam on the Senegal River. It's not a major dam. It's only 18 meters high, but it helps to store water and support irrigation in surrounding communities. And 18 meters is high enough to keep the tide from pushing brackish water back up the river, so it created upstream an ideal freshwater habitat for snails when it was built. Now, you probably remember that snails form part of the life cycle of the schistosoma trematode, or the fluke, the cause of schistosomiasis. Sure enough, after the dam was built in 1986, snails proliferated along the river, and a fierce outbreak of schistosomiasis followed. But a win-win ecological solution emerged, as documented by a brilliant series of papers from a team at Stanford and collaborators in Senegal. That solution was prawns. So these papers describe the growth of prawns, which are predators of the snails. So people there began farming the prawns. They saw a dramatic reduction in schistosomiasis. They also saw an improvement in health and well-being in people living along the river as they gained a dietary protein source and a cash crop. So here you had a bit of solutions-oriented science that fused biomedical, ecological, sociocultural, and economic thinking that really was inspiring. And this is the kind of thing that planetary health is all about. So it gives us reasons to move from this to this. It's easy to feel despair in the face of enormous planetary challenges, but despair doesn't get us anywhere. Despair immobilizes us. Hope, on the other hand, activates us. Hope is important to nurture and to propel. There are lots of reasons for hope. There's a lot of good news out there. I'm going to take you quickly through 8 reasons for hope, and I hope that I will leave you feeling hopeful. The first is the extensive co-benefits that we can harvest by advancing planetary health and tackling planetary challenges. Uh, so here are 4 elements of the green economy which we need to use to we need to deploy to tackle planetary health problems: clean energy, well-designed cities, healthy, sustainable diets, and green chemistry. Here, next to that, are some of the major health challenges we face. We would love to get less heart disease, less lung disease, less cancer. We'd love to improve mental health, control infectious diseases, reduce injuries, and achieve healthier child development. Wouldn't it be great if these green economy solutions also delivered those health solutions? Well, in fact, clean energy delivers all of these health benefits, and each of these blue arrows reflects a substantial body of evidence. This is not just a rhetorical point, it's very much an evidence-based claim. And well-designed cities that are walkable, that have mixed-use buildings, that have plenty of green space, that have active activity centers, that have strong communities, deliver all of these benefits. And healthy, sustainable diets deliver all of these benefits. And green chemistry delivers all of these benefits. So there's a very good news story embedded in the challenges of tackling planetary change. Secondly, technology is advancing. We are seeing very fast development, and battery storage may be one of the most important examples, because as we develop better electrical energy storage, we can more rapidly shift from fossil fuel combustion to renewables such as solar and wind. The economics are improving. In fact, renewables are getting so much cheaper so fast that now in most places they are less expensive than fossil fuels, which is driving the transformation to decarbonizing the energy sector faster than we dared to hope 10 years ago. Policy is maturing. Many jurisdictions, here are some pictures from the UK where I lived for the last couple of years, but look at all of these countries that have made net zero commitments. Suriname and Bhutan, bless their hearts, are there already. A number of other countries have legislated the requirements to get to net zero, and a number of other countries are in development, with 99 more countries discussing targets. Not only countries, but subnational jurisdictions like cities and states really taking a lot of leadership in decarbonizing the energy system and in tackling planetary challenges. Activism is blossoming, and this is the face of hope. This is what drives societal change. This is what drives governments to change. And over the last couple of years, we've seen a fantastic blossoming. Public opinion is shifting. More than half of Americans are now extremely or very sure that global warming is happening and are in favor of taking action. In fact, I don't know if you saw, but after the election, on election day, Fox News surveyed voters. 70% of voters surveyed by Fox News favored increased government spending on green and renewable energy. This is a transition happening in public sentiment, in contradistinction to some of the tribalism and partisanship that we have been confronting recently. Culture change is possible, and I'm showing these World War II pictures as a reminder. The public stepped up and made major changes in behavior in the Second World War in response to government campaigns. These posters could just as well be deployed now to tackle planetary health challenges. Conserve electricity and water. Use local foods. Use less meat. I mean, these are some of the same messages that we would like to get across now. And you know what? When properly delivered, these messages can change behavior. They did in the Second World War, and I think they can again. And we're seeing results. So this is not just all empty talk, but look at this. We'd love to see renewables represent most of energy use, and they don't yet do that, but the renewable share is rising very fast. 10 countries now generate more than 90% of their electricity from wind, solar, and water, and a number of subnational regions are at or near 100% renewable electricity, including, I have to say, Washington State. So lots of reasons for hope, lots of reasons for us to feel optimistic and to propel hope, not only in ourselves, but in others. The science foundation for doing this, I want to suggest, is Planetary Health, which is a scientific framework that is people-centered, systems-based, upstream-facing, equity-committed, future-oriented, solutions-driven, and hope-inspiring. We do face a profoundly altered planet with an accelerating rate of change that truly constitutes an emergency. I think the emerging framework of planetary health, as shown here, can help deliver the answers that we need. And as we do that, we need to propel hope over despair for ourselves, for our friends and families, for our students, for the larger society. Thank you very much for your attention. I look forward to the discussion.
Thank you, Howard, for an excellent, far-reaching, thought-provoking presentation. We will open this up now to questions on anybody that would like to request, comment, offer comments. Please feel free to raise a hand or wave wildly or just speak up. Okay, Howard, if you'd like to start, go ahead.
Yeah, I'll start. Thanks, Howie. That was incredible. Really, really inspiring. I want to get to this question of system science because one of the themes that seen a lot in the literature is we need to take a more of a systems approach to thinking, and that's particularly relevant to this concept of a tipping point. And you talked about the tipping point that might happen with the ocean currents. Another good example is the tipping point that happened with the crash of the ocean's fisheries, with a number of different factors that led to that. Are there other tipping points that need to be worried about where, yeah, we're seeing all these accelerated changes, but is there something that could be catastrophic, whether it's a human health outcome or any of the other factors that we have to worry about?
Yeah, there are. The picture that I showed comes from a really nice paper called something like Tipping Points Too Risky to Bet Against. And that map that I showed shows about a half a dozen or 8 plausible tipping points. So a number, and they're Earth system tipping points, not human health tipping points, although it's not hard to draw the line between the two. So the collapse of large parts of the Antarctic ice sheet or the loss of the Greenland glacier mass, both could rapidly lead to rising sea levels to the point that we would inundate coastal cities fairly quickly. And it wouldn't be an overnight kind of a thing, but it would be over the space of months to years. And that would require massive rapid migration of people away from coastal areas. Much of the human population lives in coastal areas or along rivers just upstream from coasts. So that would be a hugely disruptive thing. The Amazon rainforest may hit a tipping point because the local weather system tends to be self-reinforcing. And as you clear more forest, you change precipitation patterns and can change the forest from being a carbon sink to a carbon source. And that in turn would lead to rapid aggravation of climate change. So those are a few of the examples. The paper that just came out this week is interesting. It's a paper that looks at the Gulf Stream, the Atlantic, ATOC, Atlantic Overturning Circulation. I forget the term that the oceanographers use. But you need the Atlantic circulation to move the way it does in order to keep the North Atlantic relatively warm as warm water comes up from the South Atlantic. And as you dump more cold water from Greenland into the North Atlantic, that flow has been slowing. 10 years ago, when I looked at this, the scientific consensus among oceanographers was that's quite unlikely to happen. That's a low probability event. But the work that's coming out now suggests that it's not as low a probability as we might have hoped. So if that circulation collapses, then the warm weather that blesses much of Western Europe now suddenly gets a lot colder. And that has huge implications for agriculture and for human settlements as well. So, there's a whole field of studying tipping points in Earth systems. It's really complicated stuff and hard to get our minds around. It kind of goes back to human cognitive limits. We're not good at thinking about such big, seemingly distant threats. But the practice of hedging against threats is not totally foreign to us. We mostly buy homeowners insurance and car insurance because we know that bad things, although unlikely, could happen. And it's that sort of thinking that we need to entrain more so that we can put into place policies that would reduce the probability of these tipping points.
Thank you. Yeah, Rima, would you like to ask a question?
Yes, please. Thank you, Howard, for this fantastic talk. I wonder, with you being the self-proclaimed, clinically diagnosed optimist, what your thoughts have been. So in the last year or more with COVID, right? We've seen so many species that we thought were extinct kind of start popping up all across the globe. And, we've seen dolphins in Venice, and Delhi saw the first blue sky in ages. And it felt like there was an awakening in terms of people realizing the value of biodiversity. And also me personally, I felt like it's amazing how 1 year kind of gave nature a little bit of a break to kind of come back a little bit. So this idea of nature's resilience, human health resilience and biodiversity. Do you see a momentum now, maybe as a silver lining in COVID, with all these things happening for the field of planetary health?
That's a great question, Rima. And the answer is, I hope so. I'm going to give you a hopeful answer. If you've lived all your life in a North Indian city and never saw the Himalayas and suddenly could see them, or if you lived in an American city where the street was fully dedicated to automobiles and now it's been repurposed so that you can walk or bicycle or dine outdoors on that street, or if species are coming back, or if you realize the benefits of going to parks and green space as a restorative because you really needed it to combat your cabin fever. Well, all of those things could lead to much more popular demand for those things, for clean air, for walkable streets, for green space and tree canopy in cities. The challenge, I think, is going to be to harvest those lessons and implement them, because, of course, they come in the context of tremendous economic suffering and disruption with COVID. And so I think there's going to be an urge just to get back to normal. Not that normal was a good thing, but people are dying to get back to normal. So I think our responsibility collectively is to identify those positive lessons from COVID and to try to implement those in a long-term durable way.
So we have a question from one of our talented undergraduate students. And the question is, based on all the things that you've talked about, what post-undergraduate opportunities are there for students who want to study, learn more about planetary health?
Well, it's almost limitless. You could, if you're interested in planetary health, you could go into epidemiology or oceanography or urban planning or agronomy or civil engineering or energy engineering. The trick is whichever pathway you take, think broadly, study broadly. So if you're an epidemiologist, take an ecology course. And if you're an electrical engineer, take a sustainability course and take a human health course. I think if planetary health has any lesson to teach us, it's that the more broadly we can think and the more we can work across silos and consider all of the implications of the work we do for human health and well-being and for the planet, the more likely we are to get the right answers. So I don't think there's one particular pathway for you. Follow your passions, but whatever your passion is, be as broad, spend as much time outside your comfort zone as you possibly can. Then you'll know you're getting it right.
And just to follow up on that question of sort of comfort zones, you have, your career has transcended both the academic research, the policy, the science. I mean, sort of in many different regards here. And what might you say to our junior faculty, our undergraduates, et cetera, our students that are here? How does one, invest in policy change in terms of, taking this In the academic world, in the university, we tend to be sort of focused with blinders on, doing the primary research, and maybe don't think about how does this actually transform into usable, functional, improved public health policy. So
Yeah, that's a great question and a long discussion. I guess I just scratched the surface by offering three thoughts. One is do consequential research. And there's a whole field of writing and thinking in epidemiology that Sandro Galea, now at Boston University, has led in, called consequential epidemiology. But it's a broader point. The point is pick research topics that really matter. Instead of picking a niche research topic that has few consequences for the planet or for people, tackle a big problem, because those are the problems we really need to solve. Second, the products of your research, I think, should go beyond academic publication. I mean, so much of the work that we do in environmental health is broadly important and interesting to the public and policymakers. I'm going to posit as a default rule. There will be exceptions, of course, but as a default rule, anytime you publish a paper, also write an op-ed piece for the newspaper or for the Huffington Post or for Medium, but translate your scientific work into plain language, address the so what question, tell people why it's important, and address the implication questions. What do we do as the result of these new insights? So bring the science from academic realms into the public realm. And third, there's a lot of debate about whether academics ought to be advocates. And lots of academics feel that their job is to produce evidence, throw the evidence over the transom to the decision makers, and let other people deal with the implications. My belief is the opposite. I think that we have an obligation to be advocates. Imagine I'm a doctor. Imagine if I were trained in medicine and a patient came along to me and I diagnosed the patient and I said to the patient, well, I think I know what your diagnosis is, but I'm not going to recommend a treatment because that's for somebody else to do. I'm really here just to characterize the problem. No, not only do I want to recommend a treatment, but I want to advocate that you take the medication or get the surgery or do the behavior change because I really want you to be healthy. There is a final outcome state that I want to achieve, and I'm all about advocating for it. So I think that's the same for us. I think that it's perfectly appropriate for all of us, as the evidence supports it. Don't get ahead of the evidence, but as the evidence supports it, advocate actively for renewable energy, for sustainable renewable food practices, for clean transportation, and so on. And you can do that, as I said, by op-ed pieces, by testimony before city council or the state legislature or the federal government. You can give TED Talks. There are lots of ways that you can inject the trusted voices of science into the public debate to help us achieve a sustainable, healthy world. So pick your questions well, produce products that are generally consumable, and advocate.
thank you. Yeah, Yoshi.
Hi.
Hi, Yoshi. Long time no see.
I know, right? Thank you for your talk. I had, well, actually wanted to get your thoughts on something that pretty sure I read from an op-ed, but was this idea, and so in some silos of the science world, you kind of see this work of like parachute science, right? So as scientists kind of embed ourselves in these communities that didn't really ask for us. So how do you see any kind of parachute science or issues that could arise from parachute science when we're thinking of planetary health? And then I guess tangent to that is also the like social theory of positionality, right? And so we obviously, our decisions and the things we want to research is informed by many things as researchers, but probably, something that impacted our life. So taking those two concepts together, how can we also, how can those be embedded into planetary health?
Yeah, boy, this is a great question. You're all asking such good questions that it makes me want to stay here for a month and have daily conversations lasting all day. Planetary health is a broad paradigm, but when push comes to shove, a lot of the research is very, very local. It's the old think global, act local approach. So let me just go back to the example of nuts, of growing nuts. And if you're interested in nutrition and your work takes you to looking at the nutritional value of nuts, and you begin thinking about the upstream questions like where should we be growing nuts and how should we grow nuts, it immediately takes you to a community of the farmers who are growing nuts. And that's the farm owners, and they've got farm workers on those farms who are harvesting the nuts. And then there's a whole social context there that's really important. So if that were my field, I think I'd make every effort to get to know farmers, get to know farm workers, really understand the production process. And I'd be a little embarrassed to speak out about the nutritional value of nuts unless I had actually followed the story upstream to where the nuts come from and whose hands touch those nuts that people eat. So it's kind of an attitude of curiosity about what's upstream, of humility about the knowledge that you get from talking to the people you meet there, and then engaging in authentic ways so that you work that into the research that you do. You may find entirely different questions about nut production by spending time talking with farmers and farm workers than you would by sitting in your office, your home office these days. So I guess it comes down a lot to humility, true partnership, true engagement, and a curiosity about following your topic back upstream to where it originates. It's kind of a airy-fairy answer, but I hope it at least gets at some of what you asked about, Yoshi.
Thank you for all your insights and questions. There are several questions more coming in through the chat. Unfortunately, we've run out of time, so we'll have to send those to you and ask for responses. I appreciate you taking the time. I want to thank everybody for attending. And Dr. Frumkin, thank you for profound insights to get us all think about how we can do something that makes a difference in this changing world.
It was really a privilege to be with you all. Nice to see you all. Thank you for spending the time together. Have a good rest of the day and a good weekend, everybody.
Bye-bye.
Bye-bye.
Yeah.